Hey, welcome back. Today, we're jumping into a really fun tree traversal problem. Think of it like a treasure hunt. Our mission is to find the longest hidden sequence of numbers inside a pretty complex structure. You ready? Let's get started.
So, picture this. You're in a forest where all the trees are actually made of numbers. Your goal is to find the longest continuous path that just keeps climbing from one number to the next. That right there is the core puzzle we're going to solve today.
All right, here's our game plan. We'll start by laying out the challenge and, the specific rules for our path. Then we'll walk through the search strategy, we'll peek under the hood at the core logic, and we'll finish up with the big takeaway, why this all matters.
First up, the consecutive path challenge. Before we can even think about a solution, we've got to understand exactly what we're looking for. So let's break this problem down.
Okay, so the goal is pretty straightforward. Find the length of the longest path of consecutive, increasing numbers inside a binary tree. Now, as you can see, a tree like this can have tons of possible paths. Our job is to find the single longest one that follows a very, very specific rule. So, to find the right path, we need to know the rules of the road. What exactly does it mean for a path to be consecutive?
And here it is, the single most important rule of the game. A path is only consecutive if the value of a child node is exactly one greater than its parent. It has to be a direct parent-to-child link, and the numbers have to be climbing up one by one.
This slide illustrates that rule perfectly. A valid path has to be increasing. So, for example, a path going from a node with the value 2 to its child with the value 3, that's valid. But a path moving from 3 down to 2 is a no-go because the values are decreasing. Direction is absolutely everything here.
All right, so we know the problem and we know the rules. But how do we actually search this thing? Well, our tool of choice is a really powerful algorithm called depth-first search, or DFS for short.
Just think of DFS as a super persistent explorer. It picks a path at the very top, at the root, and it follows it as deep as it can possibly go. The moment it hits a dead end, it backtracks just a little bit and then tries the next path. It does this systematically until every single node has been visited.
Let's trace how this actually works. Our explorer starts at the root, which has a value of 1. It looks down at its child, which is a 3. Now, is 3 1 greater than 1? Nope. So that consecutive path is immediately broken. The algorithm says, okay, fine, and just treats node 3 as the potential start of a brand new path with a length of 1.
So, from that node 3, our explorer pushes on down to its child, node 4. It asks that same key question. Is 4 1 greater than 3? Yes, it is. Perfect. Our consecutive path is starting to grow. The current length is now 2.
But our explorer doesn't stop there. From node 4, it keeps going deeper to its child, node 5. And again, it checks the rule. Is 5 1 greater than 4? Yes. Fantastic. Our path just got even longer. The current path length is now 3, giving us that nice 3, 4, 5 sequence. Now, node 5 doesn't have any kids, so this particular path is done. Our explorer has found a consecutive path of length 3. What happens now? It backtracks and starts exploring all the other branches. It'll compare any new paths it finds to this length of 3, but in this tree, it's not going to find anything longer.
And there you have it. After exploring the entire tree, the longest consecutive sequence it found was that 3, 4, 5 path. So the final answer is a length of 3. This really shows you how powerful a systematic search can be.
Okay, so that was the high-level view. Now let's get into the nitty-gritty and decode the core logic that's actually powering our explorer's decisions.
The first key piece of this puzzle is recursion. What's happening is the algorithm is basically telling itself, hey, go deeper, find the length of the path below me, and then when you come back, just add 1 for me, the current node. It's how the total path length gets passed all the way back up the tree.
Next up is the most important part, the rule checker. After it gets the length from a child, the logic checks, hey, was that path actually consecutive? If a child's value isn't exactly 1 greater than its parents, the path is broken, and the code essentially hits a big reset button, starting the length count over at 1 for this new path. And finally, the algorithm needs 2 different kinds of memory. It has to track the length of the current path it's on, but it also needs a separate global memory of the longest path it's found anywhere in the tree so far. After every single path is measured, it's compared to this global maximum, which only gets updated if a new record is set.
So we've solved the problem, we've looked at the code. Now let's zoom out and really understand the bigger lesson here. Why does this all matter?
So here are the key techniques we just used.
We used depth-first search to explore everything. We used recursion to pass information up from children to parents. We used a simple check to reset our count when a rule was broken. And, super importantly, we used a global variable to keep track of the best answer we found across all the different paths.
And look, this isn't just a one-trick pony. This pattern, which people often call DFS with state, is a really fundamental approach for solving a huge range of problems. Once you get the hang of using DFS to explore while also tracking some specific value, whether it's a path length, a sum, or a maximum, you can unlock the solutions to so many complex challenges with trees and graphs. It's a real game changer.
And that pretty much brings us to the end. We've seen how to systematically explore a tree and use a set of rules to find exactly what we're looking for. So the question I'll leave you with is this. Now that you have this powerful tool in your back pocket, what other secrets and patterns are just waiting for you to uncover in the data structures all around us?